Hey class, Adam Ward here. We are getting ready to talk today about fully developed flow in pipes. And for laminar flow, this follows along with what's called the Hagen-Poiseuille derivation. So we are going to derive an equation to describe pressure drops for laminar flow within circular conduits. So we know that when flow is moving through a pipe, we know that there is a velocity and a flow rate associated, and we know that there will be a shear stress or a loss of energy associated with friction arising between the edge of the pipe and the fluid, and also fluid to fluid friction. And the result of that is that we're going to generate a pressure drop due to those losses. So our goal here is to be able to describe that pressure drop as a function of the fluid and the pipe, fluid, pipe, and flow rate. So that's what we're after today. In preparation for this video, you should have watched a lecture where we do sort of an introduction to what is laminar flow and talked about entrance length effects and how we get from still fluid to fully developed flow. And outside of that, you should have watched at least one video from YouTube to help you visualize what laminar flow is, to see just how orderly it really is. All right, so let's jump into this. Here's a pipe shown in gray, velocity profile shown in black on the left-hand side. So this is our fully developed flow. And what this pink box is trying to represent to you is if we imagine at some time that we picked that we labeled those particles and we were going to follow them as they move through space and time, what you see shown in the dash lines that says element at time t plus del t, what that is representing is in increments in time later, you will have advected from left to right, but you'll also get this deformation because the fluid in the center of the pipe is moving faster than the fluid at the edges of the pipe. So this is sort of some of the basic variables that we're going to need to apply here. Some of the assumptions that we're going to work under for the moment are that we're in a pipe of a uniform diameter. And because of that, no inputs, no outputs, no change in diameter, we have a constant velocity profile. So the velocity profile itself should remain unchanged as we move along the system. Similarly, the pipe as I've drawn it here is horizontal, meaning that there's a constant elevation. So there's no change in the z-coordinate as we move from one end of this element to the other. And so as a consequence, if we think about the energy equation here, we're not changing the velocity head and we're not changing the elevation head. What does that leave us, right? And what that means is that shear stress in the pipe or friction within the pipe is going to cause a drop in pressure. And so this is very parallel to the way that when we talk about turbo machinery like pumps, they don't add velocity, they don't accelerate the fluid, and they don't often make a large change in the elevation head. Pumps change the pressure. Turbines lower the pressure. So there's our same image at the top of the screen, and let's get to it. We are going to solve this problem by applying F equals ma. So we're going to look to Newton again, and we're going to do this within our horizontal uniform diameter pipe. We're going to assume we have laminar flow conditions, and we'll apply this analysis in the direction of flow. So along the center line of the pipe or along the x dimension in this problem. So if we isolate that little cylinder of fluid that's shown in pink to draw a free body diagram, we might have external forces like the pressure on the left-hand side pushing in. We might have pressure on the right-hand side, and I'm writing that in green, P1 minus delta P, right? So we know that there will be some drop as we move along there. So the pressure on the right should be whatever the pressure is on the left minus however much we lost. And we know that shown in purple here, we're going to have a shear stress tau. And I'm going to go ahead and try to use these colors consistently, at least on this sheet of the derivation, so you can see where this stuff is coming from. So let's start with our most generic representation. The sum of the forces in the x must equal mass times the acceleration in the x direction. And we're going to go ahead and assume that we're working with steady flow or that there is no acceleration of that fluid. right? And for fully developed flow, that has to be the case. If we're accelerating that fluid, we're tripping it up and we're getting out of that fully developed case, and it will take some amount of distance before we develop that uniform or that consistent profile again. So sum of the forces in the x equals 0. That's what we're after here. So let's do this. What do we have in the x direction in terms of forces? Well, we've got P1, pressure on the left, and that's acting in the positive x direction, so pushing to the right. And so I'm going to just draw my positive axis, as I tend to do. And an area of pi times the radius squared. So pressure pushing on a circular area, pressure times area equals force, just like it has since hydrostatics. On the opposite end of that cylinder, we have the pressure P1 minus delta P, and that's again acting on the area of the cylinder, or the area of the end of that cylinder. And finally, shear stress. We've got whatever that shear stress is, tau, which is a force per unit area, and then we need to multiply it by the area over which that shear stress occurs. Now that area in this case is 2 pi r times the length L. So where does this come from? So if we picture our cylinder, as I've drawn in this sort of yellowish color here, it has a length L, and it's got a circumference of 2 pi r. And so if you thought about that like a sheet of paper that you've curled into a tube, if we were to unroll that, the dimensions would look something like this. The length L would still be the same, and the height of it, sort of in the up and down dimension on your screen, would be the same as the circumference, or 2 pi r. So that 2 pi r L, what that's really giving you is it's giving you the cross-sectional area of the places where the fluid is in contact with the surface of the pipe. And of course that is equal to 0 for steady flow. Now we can do a little bit of solving and rearranging here. You can imagine that those P1s are going to drop out. There are pi r's in all of the terms, so we can cancel some things. And we can find ourselves with this equation written in black. The pressure drop per unit length is equal to 2 times the shear stress divided by the radius. So let's move on with that to our next slide. That's sort of an intermediate stopping point here. That's the basics of F equals ma for our flow, for our laminar flow through a pipe. All right, let's deal with shear stress next. So on this slide, we're going to start where we were, and then we're going to deal with shear stress. And so as we've been doing through a lot of this class when we did the Bernoulli and energy equation, we're going to assume that this is a Newtonian fluid. Right? And you will remember that one of the assumptions for a Newtonian fluid is that we have a linear relationship between stress and strain. In other words, we know that shear stress is going to be 0 in the middle of the pipe because for that idealized very middle portion of the flow where the velocity profile hits this uniform value, right, where it's tangent to that line that I've drawn in red, there would be no shear stress. At that exact point, the distribution is flat and all the molecules are moving in the same direction equally fast. We also know that out at the wall, our shear stress is going to be equal to something that we're going to label TW right now, shear stress at the wall. And the assumption of a linear relationship means that we can actually write this thing down. So shear stress, tau, at any radius r, so shear stress as you move away from the center line, is equal to 2 times the shear stress at the wall times the radius divided by the diameter of the pipe. Okay? So we had this relationship for pressure drop on the previous slide, and we now have a way to define what that shear stress is going to be. So we can pull those together, we can combine some terms, we can do a little bit of rearranging here, and now we can describe our pressure drop as a function of the length of pipe we're describing, the shear stress just up at the walls, and the diameter of the pipe itself. So this is okay. It doesn't look optimal to me yet, in particular because I have no idea what the shear stress at the wall would be. So yes, we're changing the way we deal with TAW, but we're not there yet. And so the way that we're going to do this is by adding some additional knowledge that we have to the problem. So in red, you see what we had on the previous slide. And you'll recall from early in the semester when we talked about shear stress and fluid properties, shear stress arises because of the viscosity of the fluid. So that's the mu, that's how easily fluid moves past itself. And then the rate of change of that velocity. So are you asking really fast fluid to move past really slow fluid? Is that a steep transition in velocity? Or is there a lot of fluid in between that can smooth out that transition? That's the dV/dr piece. Change in velocity per change in radius. So we can combine those two equations and we can separate variables. And so you ought to be able to get yourself to something that looks like this. Right? So we're taking this TAW here and we're using this descriptor of it. So now we've got our variables separated. You might imagine then that we're going to integrate, and we're going to integrate from the center of the pipe where the radius equals 0 to the outside of the pipe where the radius equals r. So we're going to integrate from radius equals 0 to radius equals r on both of those. What I've underscored in purple there, those are constants, so those can move out in front of the integration sign. It cleans up the problem to be a little easier mathematically. And what we end up with is this equation. So we've got the velocity v on the left-hand side, and that's described with that negative sign and those constants out in front, radius squared over 2, and we end up with one of those constants of integration that you'll remember from a calculus class in your past, right? And for our dealing with a constant of integration, we want to use some knowledge that we have. That's how we can find that value. So we know, for example, out at the wall, the velocity is equal to 0 because of the no-slip boundary condition. And also at that point, the radius is the pipe diameter divided by 2. So you are all the way to the edge of the pipe. And so from that knowledge, you can find out and prove to yourself what that constant of integration actually looks like. It's the pressure drop divided by 16 mu L multiplied by the pipe diameter raised to the second power. Cool. So we can plug this back in. And you'll notice that as I plug it back in, I'm doing a little bit of recombining and organizing of terms here. And we get this equation to describe the velocity at some radius r. Right? And so this is not describing the average velocity in the pipe. This is saying when you're at some radius. And so let me draw this just to be really explicit about it. So here's our pipe in black, and there's the center line. The distance r is how far away you are from the center line, and how fast the fluid is moving at that point is this VR. So what you've just done is describe the velocity somewhere within the pipe. Unfortunately, we're not really interested in the velocity at a given point in the pipe. If we were going to use this in a practical way, what we want is to describe the entirety of the pipe. And so that means summing up this equation across the entirety of the pipe. That means integration. So how do we do that? All right. We had pressure drop as a function of velocity at different points. What we want is the integration of this, right? We know that this is a complicated velocity profile and we want to integrate over the pipe. And so what we're going to do is we're going to integrate from the center line of the pipe to the outside of the pipe. So from r equals 0 at the center line to r equals diameter over 2 out at the edge. And we're going to integrate the velocity that we just had on the previous page multiplied by the area. So this is absolutely saying Q equals the sum of velocities times areas. The way this integration works is we're actually going to be working in radial coordinates here. So if you think that that's an eyeball and you're looking at the pipe on its end, what you're doing in each integration is you're sort of picking a ring within this bullseye, if you will. And this ring has some radius r, and it has, I don't know if I can even get in close enough to draw it. The thickness of that purple is dr. So what you're doing is integrating across all of these concentric circles as you move out from the very center of the pipe to the outside of the pipe. Right? So this is the integration that you're actually performing. We know a few things. We know at radius 0, the velocity is equal to vc. And all that vc means is velocity at pipe center line. So that's the velocity in the middle. And we know when you get out to the wall that no slip condition has a velocity of 0. If we go ahead and do this integration, we get a nice descriptor for flow rate as a function of things like the diameter of the pipe as well as the centerline velocity. We know the average velocity, so v with a bar over it. Average velocity is q over a. And so what we can do here is we can sort of translate our equation into an average velocity. So let's not deal with the centerline velocity, let's deal with the average velocity. So I've written at the bottom of the screen now our average velocity, v with the bar over it, is equal to pi r squared times the centerline velocity over 2. That all came from the Q definition in blue. And we still have an area on the bottom, or a pi r squared. You can cancel off a bunch of terms. And then you can go back through and actually start to plug in some of the definitions that we've recovered previously. Right? And so we have this description of average velocity, or ultimately we can get this equation of discharge in the pipe, Q, is equal to pi times diameter to the 4th times the pressure drop divided by 128 times mu times L. Okay. Hopefully this helped you see where this stuff comes from. It is absolutely the same approach we used to get at the Bernoulli equation, where we applied F equals ma, and we were very careful about keeping track of definitions and what we were and were not going to include in our problems. In this case, what you've just derived is a version of the Hagen-Poiseuille equation, and you will remember that this derivation is subject to the assumptions we made along the way. And so that's things like horizontal flow, for example. If we want to use this in a slightly more generalized way, we would go through a very, very similar process. I won't go through the painstaking detail of it, but I just want to show you where one of these new bits would come from. So if we think about our fluid here, we isolate again a little cylinder of flow within the middle. What's different when you're not horizontal is that you get some component of the weight force that is parallel to flow in the pipe. That W parallel that I've written in orange on this in this case is the component force, is the component of the weight that is acting along the axis that we're analyzing. And so that component adds something new. It's the weight of the fluid multiplied by sine theta. Of course, the weight of a fluid is its volume multiplied by its specific weight. And for a cylinder, that could be the cross-sectional area of the pipe multiplied by length, then specific weight, sine theta. So this is a new force. In our sum of the forces, we would still have pressure from the left, pressure from the right. We'd still have shear force, but in this case, you add this new parallel component of the weight. And so, sparing you all the rest of the derivation, you go through really, really similar steps. And you can recover an equation here for velocity, or you can recover a very similar equation for discharge. What's new here, for those of you paying attention, what you'll notice is it is this term right here, where the weight force is also being affected. So the stuff that I've kind of done in overbar in orange, those are the new terms that appeared because we were considering this component of weight. So what we've written here is the more generic version of the Hagen-Poiseuille equation. These are absolutely the version of the Hagen-Poiseuille equation that I would want you to use. And just to drive it home here, theta is always going to be measured relative to the horizontal. So if we have a pipe as shown here, it has a theta in black. If our pipe was flowing up vertically, it would have a theta as measured here. So we're always measuring as an angle measured counterclockwise from the horizontal. Right? That's where that theta comes from. All right, folks, that's my second lecture video about fully developed laminar flow. Following up on this, we'll do an example problem using the Hagen-Poiseuille equation and bringing back some fluid statics just so we don't forget about manometers. I hope this is helpful to everybody, and I will see you in the next video. Thanks all.